Welcome to Megasquirt Training Part 5. In this video, we're going to be taking a look at working with our general settings. We're going to have a lot to learn, so let's get started. Okay, so let's jump into this video and talk about our general settings that are going to be working with in our Tuner Studio software. So we're going to be finding we have a bunch of things that we have to define before we do any actual tuning in our Tuner Studio software. So this is going to be things that allow the Megasquirt to understand certain sensors or certain features that we want to use so that it can go in and calculate our fuel and ignition timing right. So without further wait, let's jump into the video so we can check this out. Okay, so let's get started here. We're going to be taking a look at our general settings setup for our Megasquirt. So this is going to be defining a bunch of very important information for the Megasquirt to start its calculations for control. So let's jump into that right now so we can take a look. So under basic load settings, we're going to be finding this general settings. We're going to click on this. It's going to open up our window here. Now the very first thing we're going to be finding under general settings is going to be this baro sensor settings. Now at this point, we haven't talked about our barometric sensor, but is going to allow us to reference our baro pressure at whatever elevation we're going to be at. And what we're going to be finding as we change our barometric pressure, we're going to be finding the fuel demand will change. So if you're in a location such as Colorado, and you're going to be going from Denver, and you're going to be going out of Denver, away from the mountains, and down towards sea level, you're going to be moving from something like 5,000 or 6,000 feet of elevation all the way down to 0 feet of elevation, approximately sea level. And what you're going to be finding is you have a huge change in fueling for the engine. And if you don't reference your barometric pressure, you're going to find that your tune is going to be inconsistent as you run it at different elevations. So what we want to do here is definitely utilize a barometric pressure sensor. Now, in every situation, I normally always try to wire in a barometric pressure sensor to my Megasquirt. I think it's very, very useful. It's going to make your fueling much more accurate, and you don't have to worry about having the fuel delivery or fuel demand change as you change in elevations. You're able to drive your vehicle at any racetrack throughout the country, and you won't have to worry about the tune or the fuel specifically changing and having to be constantly updated. So what we want to do here for our barometric correction, we can see we have two different choices. We see none, which disables the baro correction. We see initial map reading. This is going to be referencing what the map sensor reads when we key the ignition on. And that's going to be if we don't have a separate barometric pressure sensor wired in. Now I normally always, if I'm going to use this feature, I use two independent sensors here. And what that's going to mean is I have my map sensor for my load input, and then my barometric pressure sensor that's going to go in and tell me what that baro pressure reference is. Now we want to have these two sensors wired in because it's going to allow us to utilize when we move down in here to our primary fuel load. When we look at the actual fuel calculation type, we're going to be seeing that we can select this very specific fuel algorithm that I find to be much more accurate and much more useful for doing my tuning with. So when I selected this, we can see that it has settings change that require a power cycle to take effect. So that means that first of all I have to have a burn, so I have to burn this to my ECU, and then I have to go and cycle my power. And that's going to go ahead and take effect this change. So first I'm going to hit burn. We can see once I've done that, this need burn disappears. I'm going to go ahead, turn my power off. We're going to be seeing that it's going to be showing me here in a second. I'm offline because I've powered off my car. Now I'm going to power my vehicle back on. Wait a second, and we can see now I'm back online. So that change has taken effect. We're going to be seeing that the real-time baro port, now that I've selected this two independent sensor option, it's going to want to know where it's expecting to see the barometric pressure sensor that I've added in. So in this case, we can see we have a couple of different choices here. I have added it to my spare ADC on my Megasquirt. So depending on where you've wired your baro pressure sensor in, you're going to have to select that input port or input pin location to your Megasquirt box. So again, I have my spare ADC. Now we have this upper and lower limit, and the upper limit is going to find the highest barometric pressure that we can go and expect to see. In this case, 105 would definitely be sufficient. Now the lower limit is going to be the lowest that you're going to expect to see. So if we're at something like 8 or 9 or 10,000 feet of elevation, we can see that 80 kPa would be about the lowest. The values that are populated here already will be sufficient to use, and we can go ahead and use those. Now the next step here is going to be going in and calibrating our barometric pressure sensor that we've added. Now I've added a GM 1-bar map sensor for a baro reference. So I'm going to click close here. We're going to come right back into this, but I want to show you the process for doing this calibration. So we're going to be selecting here, I'm going to right click, go into our sensor inputs, go into our baro. And we can see that baro is off. We know it's off because if we're comparing against our map sensor, the sensor should read virtually identical on engine off, key on. That's going to be something very important that we need to know. Now our barometric pressure is going to be just referencing our atmospheric pressure, not engine vacuum or boost pressure. So as it changes, as we go in and start getting into vacuum or boost, our baro pressure will just remain at a fixed pressure level. But that's going to be very important because, again, when we look at our fuel calculations coming up here, I'm going to be showing you why that's important and why you always want to do this and use a baro pressure sensor whenever possible. So I'm going to jump into tools here. I'm going to go into map baro calibrate, click this, and we can see common baro sensors. We found, just like we did with the map sensor, we have to calibrate this. It's going to be a similar kind of sensor. I'm going to select my 1-bar calibration scale here, click burn, and I'm going to give the ECU a minute. And now, once I burn that, we can see that my baro sensor here is reading 98.7 kPa, and we can see that my map sensor here is reading 98.4. And that's very close. That's because these sensors are calibrated now, and they're referencing approximately the same because we're at the same elevation. So that's going to be what you want to see, pretty much ballpark values here. You can see they're floating around a little bit. That's normal, but you should see that they're virtually the same. So let's go click close, and we'll be jump back into our basic load settings, back into general settings here, and we can move on to the next setup here in our window. We can see that we have map sensor settings. You see the map sensor input port. This is going to be defining where we're expecting the map sensor to come in. Now, in this case, with my Megasquirt, I wired it into my map sensor input. Most of the times, you're going to be finding on a wire-in box for a Megasquirt 2, Megasquirt 1, or Megasquirt, you're going to be just wiring it into that designated input port here. Now, if you're going in and you're using a mass airflow style sensor, if we're going to be covering that type of fuel strategy and fuel calculation, we're going to be going here and setting it to the off status, not selected on map. Next, we're going to see general settings, sensor settings, and these are going to be a smoothing factor applied across all of our sensor readings. This is going to be very important because if we have something like our map pressure or engine RPM, we might find that as we're running, it's a little bit jittery. You might notice, or even your throttle position. For example, it's another one that you might see that it has a lot of fluctuation. So as you're driving, you might be steady throttle, but what might be happening is the throttle position is jittering back and forth a few percentage because you have a voltage, the circuit has the voltage being reported of having a voltage fluctuation. So we need to dampen that out. So things like our acceleration enrichment, if we're using our throttle position here, it's not trying to calculate any kind of acceleration enrichment. So as you're giving it throttle, you have to add some additional fuel. And if you have this throttle position reporting a bunch of errors constantly, it's going to be thinking that maybe you're changing your throttle that quickly and it's going to be adding fuel prematurely. So we want to avoid that. So all of our sensors have a smoothing factor. So if we have a value here of 100, that's going to be no smoothing factor. If we have a value of all the way down to 10, that's going to be the highest smoothing factor that we can apply. So we can see everything right now is here roughly at 50, 60. And that's going to be sufficient to begin with here. I don't normally change that. If we see, real quickly though, if we see that let's say our throttle position was fluctuating a bit, we could go in and lower the value down here for our TPS averaging. For example, we see it's at 50. We could go to maybe a value of 40 or 30, and that's going to dampen out that oscillation, so it's a little bit smoother application. We can see the same thing if our wideband was reading very sporadic as we're driving, which is not normally the case. You shouldn't never see that, but if it was very sporadic, and things like your throttle position here were smooth, and things like your map sensor here was smooth, and you just noticed that it was jittery, you could go and apply that same smoothing factor. So we have all these smoothing factors that we can utilize if we need to do so. Jumping in here, let's move along here to our dual table use. We can see right now we're in a single table or in a dual table mode. Now, if we're looking here at our dual table, this is going to be if we have a 2-bank engine that we want to signify that we have a VE table 1 and a VE table 2 for separate banks. So VE1 would be associated with injector 1, VE2 for the secondary fuel table would be associated with bank 2, and then they're going to have their own air fuel tables associated with each bank. So we'll have target 1, air fuel target 1 table, air fuel target 2. Most cases here we'll have a single table, and that'll be sufficient. Next, we find that we have our fuel table size. We can see that we have the ability to go in and have a 16 by 16 or a 12 by 12, and this is going to be how much resolution or data points the table will have. I always suggest you leave it on 16 by 16. We never want to have less data points. That doesn't make any sense, so I always leave this on 16 by 16. We see next here a Megasquirt temp units. We have the ability to change our scale here from Fahrenheit to Celsius, and that's going to be what's reported in our data logs when we're looking at our Megalog viewer in our data logs. I'm going to be working in units of Fahrenheit. You're probably going to be as well. If you're more accustomed to Celsius, go ahead and choose that, but I'll keep this in Fahrenheit for my personal use for tuning. We're going to be seeing here next, we see our primary fuel load, and if we drop down our selection here, we can see we have speed density, percent baro, alpha N, MAF, and ITB. Now I'm going to be doing specific videos on each of these different styles of fuel calculations, so we're very clear of how these work. Now in speed density, we're only going to be relying on our map sensor alone. Of percent baro, this is going to be why we wire it in our baro sensor. It's going to be comparing our map sensor and our barometric pressure sensor together at all times and calculating that into our fuel delivery. We're going to be looking at this again in a separate video, but this is going to be, I feel, one of the best ways you can represent your fueling, whether you're going to be in a naturally aspirated or forced induction engine. If you're going to be operating any kind of elevation change, this will be keeping your fuel delivery dead consistent without the need for an external barometric modifier fuel table. So again, as we change our elevation, our fuel delivery or fuel demand will change on our engine linearly. And then if we select this percent baro, it's going to just be compensating for that directly into our fuel table. We're going to be finding that we have an alpha N. That's going to be our throttle position base, fuel and ignition maps. We see our MAF, our mass airflow base. We're going to be taking a look at that. And then our ITB base, which is going to be specific for individual throttle bodies. For right now, let's leave it on speed density. We can keep moving on here. Our secondary fuel load. We're going to be finding that this is going to be defining what our secondary fuel table is going to be at, our VE table 2. We're going to be seeing we have speed density and percent baro, alpha N, MAF, and ITB. We're going to be seeing all the same. We'll keep this disabled here. We're not even using anything past a single table in most cases, so we can keep it, again, having the disabled feature. Okay, so next we're going to be seeing our multiply map, and we can see that it says multiply or don't multiply as choices. This is referring to utilizing the map sensor input to our fuel tables. Now, if we're in speed density or if we're in, looking at our choices here, percent baro, we absolutely want to reference this multiply map feature. Even when we're in our alpha N, this is going to put it into a hybrid mode. So it's going to be looking at our throttle position and our map sensor. And if we're in alpha N mode and we're trying to tune TPS base, chances are that we're going to do that because we have a throttle change or a rate and throttle change that is not going to be linear to our map sensor change. So we can't get a nice linear delivery of our fuel based on our throttle position. In this case, it's still going to have a map sensor as a multiplier, and you would want to leave that on there. Now, if you wanted to have a pure TPS base only with no map reference at all in the fuel calculations, you would set this to from multiply to don't multiply. But for most all circumstances, you would just leave this on this multiply feature here. Next, this incorporate air fuel target. We haven't looked at this yet, but there's going to be a target air fuel map. This is going to have the ability to do two different functions. Now, we talked about the volumetric efficiency calculation. This is a VE-based fuel strategy or fuel model in our Megasquirt. So we know in a true VE system, we're going to have our air mass divided by our target or desired air fuel is going to give us our fuel mass. And once we know our fuel mass, if we know our injector flow rate and our injector dead time, we're going to be able to correlate that fuel mass into an injector pulse width by knowing our injector data, and then we can deliver that precise amount of fuel. So we can see here in this incorporate AFR target, we have don't include AFR target and then include AFR target. So if we have it set up on include AFR target, it's going to be using a target air fuel table for our fuel mass is equal to air mass divided by desired air fuel calculation, that style VE calculation or a true VE calculation. So once we tune our VE fuel table and we have our target air fuel table set to the values we want at different load and RPM points, all we have to do to change our air fuel is go into the table and change the air fuel to wherever we want. So let's say, for example, at full throttle and boost, we had it at a target of something like 12 to 1 air fuel, but we want to richen it up. All I'd have to do if I use this include AFR target is change my air fuel value in that air fuel target table to 11.5, and my air fuel would immediately correct and deliver 11.5, and that's a true VE style system. Now, if we go in here and we select don't include AFR target, the only thing that it's going to be doing with that AFR target table is if we're in closed loop O2 operation. So it's going to be looking at our wideband input coming in, and it's going to be comparing it against the target from the table and then calculating the difference. It's only going to be using it for this closed loop style calculation. Normally, I suggest that you use include AFR target, and when we go through our calibration process from the beginning, I'm going to be showing you what to do when you tune your fuel table based on keeping this include AFR target selected here. I prefer this. This makes the most sense, and it doesn't create any more work for you during the tuning process. Now, if you decide that you wanted to start tuning with don't include AFR target in your fuel calculations, in your fuel strategy, and you go to check this on, it will change your tune. So at this point in time, because we're going through and creating a fresh map and a fresh tune, we have to decide if we want this or not. I suggest that you include it, and I'm going to be going through my calibration for my fuel tables, including this and going through our tutorials using it. But just be noting that if you do select the other option, it will change your tune. You have to retune the vehicle. We can see next we have our stoichiometric air fuel, and we need to specify this. It's going to be scaling what our air fuel displays for a proper stoichiometric. So if we're non-ethanol pump gas, we're going to be seeing it's 14.7 to 1. If we're running something like 10% blended ethanol, we'll have a value here of 14.1 to 1 air fuel. If we're running E85, we're going to be finding it's anywhere between 9.7 or 9.8 to 1 air fuel. So just be mindful when you're programming this that you have to update your stoichiometric air fuel here for the gas that we're using, because again, we're in a true VE style system, and it's going to matter for that beginning for your fuel calculation. So most cases will be at 14.1 to 1, because almost everywhere in the United States we're going to have 10% blended ethanol content. Now we can see here the next couple choices are pretty basic. Primary ignition load. If we look here, we can see that we can select different style calculations here for our spark timing map, and I am going to leave this on speed density. I only find, for example here, percent baro, that's only going to be relevant for doing our fuel calculations. We're not interested in having our baro reference our spark timing. Typically our spark timing isn't going to change that much as our elevation changes, so we don't have to worry about it. Alpha N is going to be looking at just TPS based ignition timing tables. You're usually able to reference, again, spark timing with a map sensor, so we'd leave it on speed density. Mass airflow, we have a possibility to go in and change this on our mass airflow if we're not running a map sensor. So if we're in mass airflow based, we're going to be selecting this. In ITB based, we could select this as well, but typically you're either going to be selecting speed density or mass airflow, depending on if you're in a map or math based system or modeling that we're trying to do here. Our secondary ignition load, this is going to be specifying what our secondary table is going to be defined on. We can leave this disabled because we are not using it at this time. You can see once I select it, it's going to require power cycle. So a lot of these are going to require power cycling if you're going to go and choose them. Let's go click burn. I'm just going to use that as disable. We're also going to be finding our air fuel table load. We're going to be seeing that we have use primary load algorithm. So whatever we select here for our primary fuel load, it's going to use that into our AFR target. And we'll be seeing on our acceleration enrichment, we're going to be seeing that it also has that as well. I normally leave these on this use primary load algorithm because whatever I select here is going to be used for those particular tables. So everything's going to match. It's going to make a lot more sense. So that's going to be it for our basic setup here in our general settings to begin our tuning process. We still have some more things to look at in the next coming videos, but now we've specified the most important thing that I feel is establishing our barometric pressure sensor. It does require you to purchase another sensor, but I feel that it's very worth it when we look at the advantages in our fuel table, when we select this percent baro as an option for our calculations in our fuel table. But when we get into these specific versions of our fuel strategies, we're going to be looking at each of these individually in the next coming video. It's okay
to select this two independent sensors and still have speed density at this moment just to get it to fire up and run, although I suggest that you go and select this percent baro, but when we get to that video, it'll make a lot more sense. So hopefully this is very helpful, going through all these settings. You now know what they mean, you know what they're going to be defined as, and you're going to be able to fill them out properly for your application.
Okay, so that wraps up Megasquirt training part 5. In the next video, we're going to be taking a look at setting up our ignition and cam and crank configuration. We're going to have a lot to learn, so I'll see you in the next video.